Last time we solved one problem with angle chasing, and so I want to start with several problems of angle chasing, and then progress toward other subjects around circles. Uh, the principle of angle chasing is essentially uh, two things. Well, it's this angle equality that you all know, that given an arc of a circle, the arc of a circle subtends the same angle at all points on the circle. Right? This angle is the same as this angle. They're equal. Now, this is an important fact, and this together with the angle equality of parallel lines, this sets, so having that these angles are equal, yeah, let's say this and this are equal. So parallel lines make the same angles with any given line. These two are the principal facts of angle chasing. I want to say angle chasing. Is there anything that you want to add?
Aren't the angles only equal if they're on the same side of the segment? If they're on the other side of the segment, it's 180 minus that angle.
So yeah, okay. Yeah, this is the thing to mention. In fact, I want to give an answer from this answer to this question from the general point of view that I set last time about how to view geometry as a fully algebraic structure in which inequalities are uh, not fundamental. Okay, when you look at it from this point of view, it shouldn't matter where the point is, whether it's on this side or this side, because this is not an algebraic condition on the point. The algebraic condition on the point that you're talking about, this point, is that it is on the circle. But whether it's on this side or on this side, in fact, must have analogous consequences. And one way that we can see this in terms of angle equality, we can say that the correct way to interpret the angle would be this one. Okay? Then it is still equal. It's just a matter of interpretation. But what is a more satisfactory answer? The more satisfactory answer is this. In fact, in geometry, okay, we have measured quantities, right? Such as lengths, angles, most importantly, lengths and angles, and arc measures and areas. These are the four fundamental measured quantities. The most important of them are lengths, yeah, which means distance between 2 points, well, not just distance, really, the length on a line, and an angle measure. So these quantities are in the classical way that we think about them. In the classical way that we think about them, a length is a positive real value, and angle is a value between 0 and 360, and 0 and 2 pi, we can say. In this classical way that we think about, this is not a fully algebraic definition because it's kind of picture dependent. And there is a more abstract notion of directed quantities. But I don't want to enter the details of this because this would be a whole lecture. Although it's very good to learn about this stuff in the long run. If we had more time, I would definitely dedicate one lecture to it. But you can understand the basics of this without learning the details. Basics easily. So this is something I can tell you right now. There is a notion of a directed angle or we can say oriented angle. These are, I guess, alternative words, alternative names for the same thing. Directed angle and directed length. And with these notions, an angle is something which is not something between 0 and 360, but rather it is something modulo 360. Now, this might look like it's the same thing. What does it mean? It's something modulo n versus between 0 and n. But this is something we already discussed in number theory, that it's not really the same thing. The number system modulo n, we represent it. We represent it by the numbers between 0 and n, like in number theory. But this is a representation. And when you really want to understand the algebraic properties, maybe a better way to think about them is equivalence classes. So, for example, 1 modulo 7, it's not just represented by 1, but it's all the numbers that give the remainder 1 when divided by 7, for example. Something like this. So, an angle can be considered as something modulo 360. And another notion of angle is something which is modulo 180. And in fact, these are two different definitions of directed angles. They're not even the same. Uh, so, well, obviously there is a relation between them. The one which is 180 is a more simplified version, but this is the one which actually appears more common, more frequently. Anyway, so with these, if you somehow write all the formulas, so this is the punchline. Okay, this is what I want to come to. When you write all the formulas in geometry, all the angle equality, or the length equality, or length, yeah, any formula, any equality formula which involves lengths or angles, in terms of these directed lengths and angles, then absolutely there remains no distinction between where the point is. On this side or on that side, you absolutely get the same formula. But when we just use the classical notions, so I hope this punchline that I gave should be satisfactory. I hope basis uh, for the other answers that I'm giving. So this is really the fundamental notion, because in the geometry, the whole structure of the geometry is fully algebraic, in which inequalities don't matter, and this philosophy extends to this philosophy extends to the quantities as well, quantities, angles, and lengths, and the best way, the correct way to extend it is through the directed notions. Welcome, Hassan. But when we don't do that, when we just use the classical notions, what we can do is we can always still find uh, analogous formulas with maybe plus or minus. In the case of lengths, we can maybe put plus or minus. In the case of angles, we can put alpha or 180 minus alpha. These are the same thing. And when we really want to see them as equalities, when we want to avoid alpha versus 180 minus alpha, we can always pass to the complementary angle. We can see the equalities on the pictures as well. And in some sense, this is when we do this on different kinds of pictures, we keep in our minds that all these situations are analogous. They are not different situations. Mathematically, the point being here or here, they are not different situations. Okay? What matters is that the point is on the circle, and we should say wherever the point is, it subtends the same angle on the arc, but with the correct understanding of what the angle is. When the point is here, we should take this angle, and when the point is here, we should take the angle like this, not toward inside the circle, but toward outside the circle, because we want this arc to be seen, right? In this way, all points on the circle give the same angle, and in fact, what is really nice is you can even take the point to be one of these points. You don't even have to avoid these points. You can take one of these points themselves, as the base point. And then what will be the angle? Which angle you should look at it at in that case?
It would be the angle that the second line make with the tangent line at that point.
Exactly. Exactly. You see, when you take this one, then the line becomes a tangent line. Consider A and B as the fixed points and X as the traveling point, okay? As you move along X, the lines XA and XB turn around, but they always make the same angle. And when X moves here, still XA and XB make the same angle. And one way to convince yourselves of the consistency is that we are always looking at the angle from XA to XB in the clockwise direction, if you look at it this way. This is the angle that goes from XA to XB, not from XB to XA. If you go from XB to XA, then it's counterclockwise. If you go from XA to XB, it's clockwise. And when you pass here, it's the same thing. You do the same thing. You move XA to XB clockwise and you get this angle. If you want to define the angles in this way, then you see that there is no difference as to where the point X is situated. You always get the equal angle. And even when X coincides with B, then the line XB would naturally be this tangent line. And you would get this angle, which is also equal. Okay. So this is the fundamental fact of angles in circles. And together with the simpler fact about the parallel lines, this sets the basis principles of angle chasing. So let's now start solving some problems. So there is a square ABCD. So some of the problems that I will solve today are not IMO level. They are slightly easier. They're not too easy, but I guess slightly easier than IMO level. Just to really get used to the concepts. MAN is for so there's point M and point N such that MAN is 45 degrees. Then so in the triangle MAN, these are the feet of the altitudes. There's point P and point Q defined like this. Okay. P and Q as in the picture. Let's write 45 here. Then the question is to show that B, P, Q are collinear. Okay, now I let you think about the problem. And well, think in any way that you are used to, but at the same time try to think in the in the style that I have been trying to communicate to you. That is to understand the structure, which points, well, to understand that, which points form the basis of the figure and which points are defined on top of this that we need to analyze. Okay, what the question turns around what points and what, for example, symmetries, permutation symmetries we have available in the structure of this figure, etc. If you remember, those were the kinds of uh, general thinking that we did last time. Karim, thank you for sharing in the chat. Evan Chan's notes on directed angles, and the nice thing is that on his first page, the first figure that he draws, the first figure that he drew is this one, right? Because this is a classical situation of two, kind of different, well, yet two situations, two pictures that look different.
Yeah, it's a
Classical
situation.
formulation of angles, but that actually have to be the same. If you think with algebraic logic, that have to be the same, but with classical angle quantities, classical angle measures, they look different. Alpha on one side and 180 minus alpha on the other side. So once you have this understanding, this general algebraic understanding of geometry, you know that they have to be the same. And this is the most classical situation of this phenomenon, the two different things. But we have lots of examples of this, two different pictures. They look sort of different. The formulas look different with plus or minus, etc. But essentially they are analogous and they have to be the same. So directed angles and directed lengths come to rescue in those situations. So this is how Evan Chan starts his notes as well. Did someone say something? I didn't hear. No.
Do we send our solutions when we're done, or do we wait?
No. When you solve, just send it to me. I don't want to waste too much time on these problems because these are less than IMO level. I mean, I want you to speak in the lecture. If you don't speak,
Oh,
I don't get
well,
any feedback.
yeah.
Okay?
We can find two.
It doesn't mean like tell the whole solution to not spoil it for the others, but give me the basic idea in your solution. Think about your own solution and try to uh, catch what was the insight that you had that really helped you move forward with the solution?
Um, do I talk?
What?
Do I talk?
Yeah.
Yeah, my insight was the fact that we know that APM is 90 degrees, and this is a square. So we also know that ABC is 90 degrees.
Yes.
So we can find two cyclic quadrilaterals, and it follows that they all lie on the diagonal.
Great. Yeah. So he basically summarized that. Hem basically summarized his solution. So has anyone else solved the problem? If not, I will just wait for a couple more minutes, two or three more minutes for you. So to complete fill the gaps in this. Okay. What Ethem has said is essentially this 90 degree here together with the 90 degree here is supposed to give me a cyclic quadrilateral. And by using this cyclic quadrilateral by using using the angle chasing through this cyclic quadrilateral and other analogous things, ultimately I should get that P is on the diagonal and Q is on the diagonal. Well, in fact, if you prove that P is on the diagonal BD, Q is analogously on the diagonal BD. Or now let me actually start from zero and start thinking about the problem like this. Okay, what's the structure here? There is a square. In the beginning, there is a square before defining any other points. Now, if you just have a square, all 4 points are on equal footing. There's permutation symmetry. But here, for the rest of the defining rest of the picture, the point A is distinguished because points M and N are on the lines BC and CD. So point C is distinguished, and point A is the point which is opposite to it. There is no way that I can permute A and C with any other points they have special role. I mean, if I try to permute A and C, the other points would move around. I mean, the figure would not be analogous. Right? A is a special point, C is a special point on the circle, but B and D have equal roles here. So it doesn't really matter which one is B, which one is D. We could call this one B and this one D. Then simply this one would be M, this one would be N. The points, notice what, to really make sure that you understand what I mean, here's what I mean is this. We are not changing the point. When we talk about this permutation symmetry, which is very important in geometry in general, permutation symmetry, what I really mean is that we don't move anything from where it is. All the points remain where they are on the plane. All the lines remain where they are. The figure is fixed to the plane. Nothing changes. It's just that the labels are permuted. The letters, the names of the lines, the names of the points to be permuted in a way that all the information still holds. When you can do this, when you can fix the same figure while changing the letters, this gives information about, in some sense, information about the structure. For example, let's see this case, this problem. It really shows it. Well, one way to see it is, in fact, if you just delete the labels from the picture, but don't delete them from here. Read the question. Read the question as it is, and look at the picture without the labels. Can you figure out which point is which? When you look at this picture with no names of the letters, but when you still read this, that ABCD is a square, this should be more detailed, ABCD square, and M is on BC, and N is on DC. First information is this, and then MAN is 45. Well, PQ, okay, we should give the information in more detail, but I don't want to write. Anyway, from this, you could understand that this is the point A. So there is no way A is permuted. And this is point C likewise. However, B and D can flip. So one of them should be, one of these should be B, the other one should be D. But once I put which one is B and D, then the rest is also put. If this is B, then this is M, this is P. And this is D, this is N, this is Q. Otherwise, I can just flip. I can put B here, D here, then M would be here, N would be here, Q would be here, P would be here. But then what happens? What does this, permutation symmetry tell me about this problem? About the permutation symmetry of the given things. It should be reflected in the conclusion of the problem as well. If I can replace B by D, P by Q, and Q by P, B, P, Q are collinear should automatically mean D, Q, P are collinear. All right. So I want to write a first thought. The problem has permutation symmetry such things are called permutation symmetries. B and D and P and Q, M and N to be flipped. And when you do them simultaneously, so this is just a single permutation, single involution. And when you do the same permutation again, it just brings you to the identity. So this is just what is called, order 2 symmetry, which is typical. So the problem has this permutation symmetry. Thus, if BPQ are collinear as a statement to be proven, not just as an information. If this is given as an information, it's a different thing. But in this case, it is asked that it is proven. It's asked to be proven, which means this follows from the already given things. This is not extra information. If this is given as extra information, then from the extra information I cannot derive another information. I cannot say, for example, in the problem, suppose this doesn't follow from what is given, but it is just given by itself as an extra given things in the problem. Then from this I cannot say, D, Q, P are collinear. In fact, it would, what would it do? It would break the symmetry. After this, the symmetry would be broken. However, in the problem, it asks us that this follows from what is given. So no symmetry can be broken, which means if P, P, Q are collinear, let me write this clearly. If we can prove that B, P, Q are collinear by any means, okay, given any proof, anyone gives me any proof that B, P, Q are collinear. If the proof is correct, I can do the same proof analogously and prove that D, P, Q are collinear. If we can prove that B, P, Q are collinear, then we can prove that D, Q, P are collinear. Right? Do you agree with this?
Yes.
Yeah, this is the first thought in the problem. Look, I have not done anything. But this this gives me an insight about the problem. So it says, okay, I am supposed to prove that these 4 points are collinear. So the problem didn't reveal it to me. In the problem formulation, they didn't reveal that the points P, Q are on the diagonal. They only asked that the line PQ passes through B. They only asked that these 3 points are collinear. However, by some simple thought, I understood basically this line PQ is a fixed line. It doesn't change by permutation. So if it passes through one of the corners, it has to pass through the other corner. So really what we really need to prove is that these points are on the diagonal. So with this insight, I have an approach to the problem. Okay, what should I do? Maybe a reasonable way is to prove this separately for P and Q, because that would be easier. Look, why would this be easier? Because points A, B, C, D is at the basis of the figure. Those are the simple points. And then come the points M and N. They are also on the sides of the square. So they are also kind of tractable. And finally, at the final stage, come the points P and Q. And the problem is about the points P and Q. So we really need to understand the points P and Q. Everything that we understand about P, automatically we understand about Q. They are analogous points. However, the problem asks us to prove that these 3 points are collinear. So for this, I need to analyze P and Q at the same time. So I want to understand the point P. Analogously, I want to understand the point Q, but I need to analyze them at the same time, which is another challenge. However, if I change the problem and if I try to prove BPD are collinear and BQD are collinear separately, then I don't have to analyze P and Q at the same time, which saves me from one challenge. I can analyze them separately now. P is on the diagonal, Q is on the diagonal. Now these are completely analogous statements, so it is enough to prove one of them. Okay, so these are, let's say, first thoughts. This would be the second one. First thoughts. This is one. The second. Then let's prove P is on BD. Let's just focus on proving this. Analogously, we get Q is on BD. you can immediately argue that this is analogous because of this permutation symmetry, because the line BD is just this line. Or you can just do the same proof. You can repeat the same proof. That's fine. And this will conclude. Notice this has completely saved me from point Q, because now this is the statement that I am focusing on. I just need to understand the point P. And I suppose you have probably understood Adham's solution. So what Adham has said is this: using this 90 degrees, we can see that P is on a certain circle, and we can do some angle chasing. So let me write the solution. So even if you have not, started thinking about the problem like this, you can of course still do it, because this is not a very difficult problem. However, this kinds of thoughts is very general. It really warms you up to any kind of geometry problem almost that you have. I mean, and you don't lose anything. If you don't get anything from this thought, it's still fine. And sometimes you don't find any permutation symmetry. It's okay. Some problems don't have any structure like that. However, there is always something when you start analyzing, which points I need to further understand, which properties of the points here I need to understand, etc. When you focus on them, as we did last time when we solved the problem from the mock exam. For example, you focus on a point and you extract that part of the picture, that part of the figure, and you draw it in a separate picture, and you try to get information from there. Those are completely general things. So for this solution, what we see is that this 90 degrees and the 90 degrees here shows that AP, and B are cyclic with diameter AM. The circle with diameter AM passes through P and B, which means the angle PBM equals angle PAM. So 45 degrees. APM is 90 and ABM is 90, which means PBAM, well, let's write the points in order, PMBA cyclic. So from this, PBM, angle PBM equals PAM equals 45. When this is 45, of course it is on BD. Now this is how the solution starts. This is the first step of the solution. To complete the solution, you should prove that Q is on BD. As I said, you can either say that, well, how do you prove Q is on BD? You can either write this sentence: the problem has permutation symmetry, B to D, P to Q, M to N. And this is a very professional sentence. If you write this is really good. And because of this permutation symmetry, automatically Q is on BD. You can write it like that, or you can just repeat the same proof with the analogous things. Okay, what's the analogous things? A, Q, and D are cyclic. You still think about the permutation symmetry in your mind, but you don't want to confuse the reader, maybe, who may not be a professional. But hopefully, grade coordinators are mostly they are professional enough. So you simply write A, Q, N. Every time you see P, you just write Q. For M, you write N, and B and D you flip, right? AQN is 90 and ADN is 90, which means QN. Look, I'm not even looking at the picture. I'm just replacing P by Q, M by N, B by D. I'm so sure it will be automatically true. I'm not even looking at the picture. So this will give me QDN equals QAN, which is 45 degrees. So Q is on BD. Right. And then finally you say consequently B, D, P, Q are all collinear. This is how you can write this complete solution. Do you have any question? Or let's just pass through another problem. So there is a circle ABC and a circumcircle. The circumcircle. The point D is opposite to A, okay? AD is diameter of the circumcircle. This is given about point. So point D is defined to be the opposite point. Then so there is point K on this. Okay. And point E on this, which is different from C. So K is on BD and E is on AC with E different from C, such that KB, KC, and KE are equal. Well, think about these conditions as to sometimes points are defined, points are given with conditions, and in those cases you should think, do those conditions define the points uniquely? So the given conditions, given equalities, do they define the points, or do they, for example, possibly give two different points? You should think about those, okay? To really understand the conditions, show that the circle BKE is tangent to the circle ABC, to the which is this circumcircle, the shown circumcircle. So the circle here that I don't want to draw really to not complicate the picture, but this circle is, we want to prove that this circle is tangent to the circumcircle. Okay. All right. So start thinking about the problem. By the way, on this problem, I want to draw alternative pictures to show you this general idea, general idea of algebraicness of the Euclidean geometry. So how can we draw alternative pictures in terms of the positions of the points? So ABC, the square ABCD is given. Nothing is going to be moved there. So I mean the points M and N. So here in this picture, they are on the segments. When you put M on the segment BC, you automatically put N on the segment CD, and the picture becomes like this. One thing you can do is you can move M outside from this side or from this side, and then try to see what happens. Just for the sake of expanding our horizons, okay? Alternative pictures. As I said, this is the kind of thing that you can do before solving a problem. And sometimes it gives you an idea. Not in the very easy problems, but sometimes, when the problem is not very easy, it gives you an idea. Drawing alternative pictures. So here M can be taken like this. So by the way, when M coincides exactly with C, so those are the degenerate situations which can happen. What happens to N? So you can think of M and N as points which move together with each other, okay? This is the way that you can think about M and N. A, B, C, D is the fixed frame there, and there is a moving point M and a moving point N, but they move together. So when M hits C, N hits D. Okay? Do you see this? If you move them in this direction, if you move M toward the right, N moves up. When M comes and hits C, N hits D. Do you agree?
Yes.
Because of 45. And when M goes out from here, N goes out. And similarly, if you move toward the left, when M hits B, N moves down and hits C. And if M moves out, then N moves out from down. So those are similar situations, so I will just draw one of them. So N will be like here, okay? In this situation, P should be like maybe, where should be P? P should probably be, yeah, probably A and M becomes more than 90 degrees, I suppose, in this case. That's what it looks like, and P becomes here. You see, yeah. For it to be on the diagonal, it has to be like this. But N on AM is like this. For example, points P and Q are still on the diagonal, but now P has moved out. And maybe if we move M further out, I don't know if Q would ever move out. Maybe not. Yeah, probably not, yeah. No matter how far you move M in this direction. If you move M in this direction, of course, then Q goes out. So the motion of Q, so as M and N moves along their lines, P and Q move along the diagonal. Their motion is has a different behavior. And there are topics in Olympiad geometry which use the concepts of projective geometry to analyze the relations between points by imagining them as moving. Okay, to analyze the relation between the points, one imagines that they move in a certain way, And to analyze the motions, one uses the notions of projective geometry, and this has been developed recently uh, as a topic, as an advanced topic in Olympiad geometry, and people use this in solving difficult problems, solving small parts of difficult problems. There are handouts, no, there are basically Olympiad notes that you can find online about these things as well. But those are not for the, let's say, IMO level 1 or level 2 problems. Maybe level 2 to some extent. But so for you, it is not relevant in the short term. I just wanted to bring to your attention that all of these topics are really uh, stuff that people are interested in, and they further develop. Projective geometry is, by the way, algebraic geometry. Okay, it's a special case of algebraic geometry, which is relevant in Olympiads. Okay, anyway, yeah, let's look at this one. And hopefully, after solving this problem, let's move away from angle chasing. Let's start discussing other things. So, okay, what have you thought so far? We want to prove that two circles are tangent. Well, do we have any idea where they are tangent?
They are tangent.
Yeah, at the point B, right? It is explicitly given. So this makes the problem easy. This part easy. Sometimes there are problems in which they ask you to prove that a circle is tangent to a circle or a circle is tangent to a line, but you don't know the point at which it's going to be like that. And then usually in those cases, the proof is based on, well, not always, but usually the proof is based on discovering that point, first of all. You discover that point. For example, you want to show that the circle is tangent to a line. You somehow discover a point, define a point, and you know that you somehow prove that that point is on that line, and the point is also on that circle. So you prove some collinearity and some cyclicity, and then by angle chasing maybe or other methods, you can prove that they are tangent at that point. But here, the point B is already given. So how can we how can we prove that they are tangent at this point? Being two circles being tangent at this point means they are tangent to the same line. So there is a unique line which is tangent, which makes a unique angle with the line BC or unique angle with any other line. So what we really want to show is that these circles, the circle BKE is also tangent to the same line. So it's one of these circles. So let me draw a general picture for you of circles that are tangent at a given point. So when you have a circle and a point, all the circles that pass through this point and tangent to this circle form a nice picture like this. They are all tangent to this line. In some sense, yeah, this is about where the center of the circle is. Once you know that the circle passes through this point, as the center moves along a line, the circle gets bigger or smaller, or moves to this side. But as you can see, all of these centers are collinear. Usually it's not practical though to think about the center. It's not a practical thing in the Olympiad because the center is not really, well, to try to define the center of the circle BKE is difficult because you cannot really study the center. You have to have other ways. But just to show you the complete picture, so this is one example of a family of circles in which the centers are collinear, but not only the centers are collinear, but the radius also moves in a special way. As the center moves, the radius also changes according to this, so that the family satisfies one nice condition relative to each other. They are all tangent to the same thing. This is an example of what is called a pencil of circles. Yeah, I just wanted to give you this general picture. Let me move this actually, because it's gonna be pencil of circles, all tangent to each other. Anyway, so here we don't really have so many circles. We just have two circles, right? So we want to show that BK is. So any approach, anything that you have thought about? So in some sense here, we are trying to understand the circle BKE, right? Because the circle ABC is sort of given. The triangle is given. The circle is given. The point D is just a point opposite to A. There is not much to think about that. There are the points K and E that we need to understand. These are the 2 points that we need to understand, and they are defined by this condition. So let me ask the question that I raised. Does this condition uniquely define the point K and the point E?
Yes.
So how do you know? How does K how is K defined from this condition? And how is E defined?
It's the intersection of the perpendicular bisector of BC and with the line BD.
Exactly. Yeah, exactly. The condition KB equals KC. Just this condition is what defines K uniquely, because this shows that K has to be on the perpendicular bisector of BC. And it's already known that it's on the line BD. So there is a unique intersection. So this is the point K, which is defined uniquely. However, point E, it should be defined by the condition that KE is equal to these
Yeah, but
things.
it could be in the other side.
Well, no, think about it. So this E is defined in terms of its distance to K. So there is a circle with center K passing through BC, right, with this radius. Center K and with this radius. So it is this circle and the intersection of this circle with line AC. So this is also unique.
Oh, yeah, I see.
This is also unique because this circle has
Yeah.
two intersections with the line AC, but one of them is already C. So this is the other intersection. Okay.
Yes.
So on the line AC, well, another way to think about it is if you drop a perpendicular from K to AC, then C and E must be symmetric here. If KC and KE are equal, if they have equal lengths, the perpendicular that's dropped from K to AC must be the midpoint of C and E. So there is only one point E, which is like this. Okay, so let's write these things. K is the intersection of the perpendicular bisector. BC with BD. Is the what is called second intersection of a circle. When you talk about the intersection of a circle and a line, if one of the intersections is obvious, the other intersection is called the second intersection. Is the second intersection of the circle with center K passing through B and C. With the line AC. Okay. Just thoughts. All right, so these are just the basic definitions, but the problem still remains. We need to understand these points. It's not just these
Yeah.
definitions. We need to understand these points in a targeted way to prove that this circle is tangent to a particular direction. What is
Actually, yeah,
yeah.
we can do angle chasing and show that uh, the angle that this tangent makes with BD is the same as BAEK. So we want to show that BEK equal to BCD, which equal to 90 minus angle C. And I think we can do that by angle chasing. It's not hard.
Yeah, okay. Yeah, let's try to do that. Exactly. So, good. So the first thought is, would angle chasing work in this problem? For
Yeah.
for this to really work, for angle chasing to work, we need to. So we have this tangent line. So for this tangent line, we of course know what angle this tangent line makes with BC, for example, the line BC or line BA or any of them. For example, but when it comes to BEK, one way to do, I mean, how can we do? We should either look at this line. So we should try to prove. So if you want to do angle chasing with this line at this point, I should look at the angle between this line and between one of these two, BK or BE, right? So there seems to be two possibilities. Well, with angle chasing approach, say you just have the points BEK in general, and you have a certain line passing through here, and you want to show that this is tangent, right? So what can you look at? You should look at the angle that this tangent line, the line that is gonna be proven to be tangent. You should look at the angle between this and what else? BK or BE, right? So you can look at this angle. In this case, you should prove that it is equal to this angle. The other alternative is to prove that it is, this is equal to this. So we have to, these are the angle chasing approaches. If they are possible, if they look possible, we should follow that. We should go through that. Try to do that. But we should be smart. Which one looks more feasible? In terms of understanding this angle or this angle, in terms of understanding the angle, with the red angle or the green angle here, to understand which one is more feasible, the question becomes this, this light blue line is not an obstacle. We can easily write angles with this because we already know it is tangent to the circumcircle. We can easily write angles with this. But to understand the angle, you need to understand two lines. So the question is, which line is better? Is the line BK or BE? Which one is a better line that we can understand?
I think BK because
Yeah.
yeah,
Yeah, that's
because
definitely true. The line BK, because it's already given in the problem, because it's the line BD. Because
yeah,
we know things about it. AD is diameter, so in fact this is 90 degrees. Right? So definitely the red angle is something I would prefer. Because the line BE, I don't even have it immediately in the problem. But we should also be careful about, if I'm choosing the red angle here, I will need to try to understand the line BEK. Sorry, the angle BEK. Do I have any idea about this that I can do? What is the
yeah,
point E in relation? As you can see, point K is more fundamental because it's the one that is defined first, and then E is defined in terms of K. But when E is defined, do I have a way to understand the angle BEK? I should look
Yeah,
at yeah, what is it, Karen?
it's equal to ABK because they are isosceles triangle.
It's equal to what? EBK.
Yeah, it's
Yeah,
equal to
but
angle
then
EBK.
what is EBK?
EBK we can find CBK, so it will be equal to 90 minus angle B.
But then you will need to find EBC.
Or,
What is EBC?
or actually we can do it alternatively. We can find angle BKC, and then we can find angle EKC, and so we find angle BKE, and so we find angle KBE,
So what
and
is
angle
important
K.
here is, yeah, I will try to follow your angle chasing again, but I want to, first of all, remind you of what is our goal. Never forget about the layer structure. So there is the basic layer of the figure, and then point K is defined, and then point E is defined. Now we are trying to write an angle about E, BEK. So I have two red angles. I'm trying to prove that they are equal. Okay, I will need to write these two angles. Which one is the more difficult angle? This one is the more difficult angle because it contains the point E. This one doesn't contain the point E. This one is in fact very easy because it's just the angle between the tangent line here and the line BD. It's something directly about the triangle figure itself without points K and E. With no definition of point K and E, I can write this angle here. That's fine. So I need to write this angle. When I try to write this angle, I want to make it equal to a better angle, to an angle that I can understand better, which means to an angle that is saved from the new definitions, the point E in particular. If I can write this angle in terms of something which doesn't have point E in it, which also doesn't bring any new points, okay, which is less complicated than this. So if I can reduce this to the point, well, to the triangle itself and the point K, this would be progress. But if I just keep writing the angle, so in angle chasing, this is really the trick. How do you know that you are progressing and you are not moving around the circles? It's sort of like you are in a city that you have not visited before and you are trying to navigate yourself in the streets. You can maybe turn around in circles and come back to the same point. How will you avoid doing that? Well, if you have a signpost that is far away and if you always move toward there, then you know you will not come back to the same point, right? So this reminds me of a fond memory. There is once I think I was in high school. At that time, I lived in Ankara, but I would usually not go to the downtown. Very rarely in my life, like once a year or less than that, go to the downtown. Once I went to meet a friend in the mosque, which is situated on the hilltop. Uh, I know the district where the mosque is located, so I went there by train, by metro, but I don't know to find my way through the streets to find the mosque. So what I did is I just always walked uphill. You know, at every junction of the street you come, you just choose the direction which goes up. And this with this algorithm, you have to end up at the hilltop. But it of course doesn't work when you want to come back. Then you have countless opportunities. So it's sort of like this. So here your goal is to save yourself from the point E. Okay? When you write this angle. So for this, let's extract the part of the figure which defines E. Namely, E is on the circle with center K and passing through the points. Well, E is on this circle, but E is of course not an arbitrary circle here. So sorry, not an arbitrary point. We also know the direction of EC. Okay, we know that E is on this circle, and we know this line. So somehow, even if we cannot save ourselves from point E completely, if we can bring it in such a way that we only have line EC and we don't have line EK or line EB, then this is good, because then line EC is just line AC, then we can save ourselves from point E. So in some sense, these are the bad lines that we don't want to have. When we write the angle chasing, our purpose is to save ourselves from these lines using this circle. Okay, so with this explanation, now can I listen to your angle chasing, Kerem? You said BEK equals EBK. Yeah, sorry. Yeah, what else?
We have also angle KBC equal to BCK, which equal to 90 minus angle B in the triangle ABC.
Okay, probably your angle chasing. I will probably simplify it. Okay, let's look at it. But I will first listen to it and then try to simplify. So you said which one? BCK equals.
BCK to angle equal to angle BCK, which equal to 90 minus angle B.
Yeah, 90 minus angle B. Yeah, because of this 90 degrees here. Yeah, the
Yeah.
90 degrees is 90 minus B, and this is equal. Okay, this green angle is 90 minus B there. Okay,
Yeah. So now we can find angle BKC
angle
equal to,
BKC. Yeah, 2B, right?
yeah, to angle B. And now we can find angle KCE, which equal to angle C plus 90 minus angle B.
Yeah.
So angle KEC is also 90 plus angle C minus angle B. So now we can find angle EKC, and we know angle BKC, so we know angle BKE, and we can then find angle BEK.
Okay, yeah, I understand what you mean. So what you are doing is something completely general. Let me do it in generality. Okay, on the first page, and just apply it as a lemma here. In fact, let's go to the first page. In fact, we have not even proven this, right? Let me first prove this and then prove another thing, which is basically what you're saying, okay? So let me prove this thing about the circles, uh, which is very easy, but so proof is when you have point A, B, put the point O, put the point X. Well, in fact, let's do it. Let's not do it like this. Let's do it like this. Let's just draw the triangle and say, okay, we have X, A, B, and point O. Okay, so there is the circle. So what I will show is this. This angle alpha is the same as this alpha, because you know OX, OA, OB are the same. This beta is the same as this beta. This angle is the sum of these, right? Alpha, beta, alpha, beta. Because alpha, beta, well, because you know in this quadrilateral, the remaining angle is the complement of this, so it should be 360 minus sum of alphas, betas. So this shows that AOB equals 2 times AXB. This shows that when you put the point O here, this AOB is a fixed angle. So no matter how you move x, 2 times AXB is always AOB. So this is the proof. But in this proof, I used a particular picture in which the point O is inside the triangle. So if you move x like this, point O becomes outside. And if you move x like this, point O becomes outside from the other direction. But in all these cases, this formula holds. So we have to maybe prove this in different pictures. But in reality, I mean, as I said, when you do this with, when you do it fully professionally with directed angles, you don't have to prove it in different figures. But let's just show some of it as examples. When O is outside like this, you should still have the same figure. I mean, well, you have the same figure, same picture somehow. Well, this is alpha, and this is beta, this is beta. So what remains here? You can show that this should be 2 alpha minus 2 beta. Yeah, how can you prove it? Well, similarly, you know, by maybe looking at this like if you just say, okay, this is alpha minus beta here, and this will be say this will let's put gamma here, for example, alpha minus beta plus alpha plus gamma equals 180. So from this you can solve gamma, and sorry, this is gamma and this is gamma minus beta, right? So alpha minus beta, alpha, gamma minus beta. So from this you can solve gamma, and then you can use that gamma to find this, which still comes to the same thing. So as the picture changes, this, you know, plus or minuses change, but the statements are analogous. They cannot change. But when O is on this side, for example, when AB is like this, then this time, okay, one should be careful. Then this time, this angle AOB is 2 times AXB. There's always some shown AOB is 2 times AXB. And if you compare all of that to this figure, you will see it's always, but if you look at, if you want to look at this AOB, then you should take the complementary AXB. If you take this one, this AXB which is outside, then 2 times that is of course equal to this AOB inside. So if you look at this one, this fixed AOB, if you look at this angle fixed AOB, it is 2 times this AXB, and this shown AXB. Now, let's write another statement, which is a typical lemma, well, classic lemma about the angle that this makes this angle. Okay, O is the circumcenter. So this angle in any circle, okay, the angle that a side makes with a radius is, what is it equal to? BAO equals 90 minus C. Why? Because if this is C, this is 2C, and this is 90 minus C, 90 minus C. This is an important lemma, and it's self-evident. I don't need to prove it because, well, this is already the proof. But even in other figures, sorry, other pictures, it finds itself like this. Even when somehow, O is outside like that. Okay. Still, this is 90 minus C. Or when O is outside in this way, then C is more than 90 in this situation. So what really happens is this is C minus 90. Okay, you can convince yourself that this is true. In all the different pictures, we see the same theorem. So this is when O is outside still, this is 90 minus C. This is not, again, picture dependent. As this is not picture dependent. All the theorems in geometry, they fundamentally survive under different pictures. So, okay, let's go back to our problem and let's listen to the angle chasing that Kerem has said. It's essentially this. So, Kerem wanted to write the angle BEK. So, his idea was to say, well, let's write the angle BKE. Okay. And then, if we can write this angle, the rest in this triangle BEK, if this angle BKE is alpha, what remains is 180 minus alpha, but it has to equally divided by 2 for two angles. This is the idea. But to write this angle, his idea was to write BKC and EKC separately and subtract. How do you write BKC and EKC? How do you write BCK and ECK from this? But essentially, all this that is done is simply equivalent to immediately putting BKE equals 2C. This removes all that complication. Okay? Do you see this, Kerem? Or let me try to
Could
show
you
it
repeat?
again. Let me try to show it again. So wait. So what you told me, Kerem, is this. You told me the angle. Well, you said you can write the angle, this angle, and you can know this angle. And by knowing both of these, you can know both of these. And automatically you can know the difference here. Which is the same thing that we do like here. Okay, alpha and beta. By knowing alpha and beta, from this alpha, for example, we can know that this is 180 minus alpha. From this beta, we can know this is 180 minus 2 beta. So the difference is 2 alpha minus 2 beta. So it just remains that this angle is 2 times the angle AXB. So what you are really doing in terms of obtaining the angle BKE by subtracting these two angles, by using these two angles, is really just to say ultimately that this BKE is 2 times this angle here. You don't even need to know BCK precisely. Okay? This is simply Mostly angle chasings that you do can be simplified, guys, by the way. This is C and this is 2C. And this gives me, this is 90 minus C, 90 minus C. This was your idea. And in fact, I don't even need to go through this 2C because this is a lemma directly. This is the lemma that I did here. Okay. This is 90 minus C lemma. So all those angle chasing steps is a single thing, that the angle BEK is equal to 90 minus C. So I immediately save myself from the point E by writing this angle. Now what remains is to prove that it's equal to this angle, and which hopefully we can do to prove that this is 90 minus C. I already have 90 degrees here, so I need to prove that this is 180 minus C. I need to prove that this is C, which is true by tangency. Okay. So I don't need this anymore. So if we go back and summarize, have you seen what we did? First, our first task was how to define the points and to understand the layer structure of the points. And then we thought about, can we do angle chasing? And with angle chasing, the good idea, so we said, there are these two ideas. So which one is better? Which angles are more easily handleable? We understood that this red angle is good. So we need to understand this red angle. And to understand this, we focused on the definition of E. And we found this angle from this small sub-figure which is extracted. And then we go back to the original problem and we can now write the solution. For the solution, I would start from here. Since I would say K is the center of circle EBC, we have angle BEK, well, because of the center, this is equal to 90 minus ECB, which is 90 minus C. On the other side, let L, okay, this L is the line, okay, to be able to write angle with this. But maybe it is better to put a point on this line so that we can write the angles better. Let's put some point, useless point X. Okay, it doesn't matter where the point is. We will just use this to write angles with this line to be able to give a name to this line. Because there is only one point on this line that we know. Now we want to call this XB. And we want to be able to write the angles XBA, etc. Okay. Or maybe we want to write this one, right? So we want to put the point X here. So uh, let X be a point. Let X. Of course, as I said, if you do angle chasing with directed angles, it doesn't even matter where you put X. Here or here, it will give you the same angles. Because algebraically, there is no difference. Let X be a point such that XB is tangent to ABC. This is a point as shown. From this, what I know is angle XBA is 180 minus C. Okay. Angle XBA is 180 minus C. So let's move this guy from here. So the next thing we would do is to look at the angle ABK is 90. So this we know. Therefore, angle XBK is 180 minus C minus 90, which is 90 minus C, which is equal to BEK. So this shows that XB is tangent to BEK. See? So in all Olympiad problems, well, especially in geometry, geometry has a very rigid and explicit structure. It's like a very big city, and you are trying to find your way through the streets of the city. And once you have signposts, once you know where you want to go, you can find how you want to go there. Okay, these two are enough for angle chasing problems. Do you have any remarks? Now I want to teach you about power of a point.
I'm already aware of the theorem, and I think other people are aware of it too.
Sorry, what?
I already know the theorem. Can we skip to problems or something?
Power of a point? No, there is a lot that I will tell about this. I mean, even if you know about the definition and the theorems, uh, it is good to review the subject from this abstract, let's say, perspective that's usually omitted. So let's define. Okay, I can imagine that most of you at least know the definition. That's for sure. However, there is more more about this. So power of a point. Power of a point x with respect to a circle gamma. Okay, gamma. Let's say gamma is defined. So a circle, one standard way, the best way, let's say, to define a circle is through its center and radius, right? The circle is, let's just write it like this: circle is defined. I mean, let's just use a notation like this: circ OR. So here, these are our objects. So we have the point x, circle gamma, which are defined in terms of a point O and the value r. R is the radius, so we can think of it as a positive real value. But for algebraic purposes, even other numbers can make sense. But we are trying to understand the geometry here, of course, with pictures. So radius is a positive real value for us, and O is a point. And we have the circle gamma defined by this. What's the definition of power? Well, let's use notation like this. Power with respect to the circle gamma of point x, by definition, is xo squared minus r squared. So here the center and the radius plays their roles separately. The role of the center is that in the definition of the power, one looks at the distance to the center. To understand the power of a point, you just look at the distance of the point to the center. It's really defined in terms of the distance. What really all that matters is the distance of the point x to the center of the circle for part of the formula, and radius just enters as a constant value that shifts this. This is an offset. You just subtract some positive quantity from the squared distance. So very simple definition. But this is not just a mere definition. It has significant geometric consequences, and that's what matters. So let's try to show the geometric consequences of this. important facts. The first important fact is this one. If you try to understand this in terms of geometry, in terms of the picture, for example, let's draw this picture and let's draw the line XO. So this is the diameter of the circle, and let's look at the intersections P and Q. You can see that XP is XO minus R and XQ is XO plus R. You can see that power of X, I'm not writing the circle because it's the circle, this is equal to XP times XQ. But the really nice thing is that this doesn't have to be the diameter. You can draw any segment, any line that goes through X and intersecting the circle at any 2 points A and B, and you have the same thing equal. Okay, any of these lines give me the same quantity when we multiply XA by XB. So this is why this power definition is somehow important, the first geometric understanding of this fact. However, one should still not forget about the algebraic formula, because somehow the degenerate cases are also important. One can think about the degenerate circle with radius 0. Just point O, the circle with given center and radius 0. One can say that the power is just distance squared. This is also within the definition. So the definition is more general. But more practically, we of course think in terms of real circles. And for a real circle, this is the picture that we have. So how can we prove this? The proof is easy. We want to prove that given X and any 2 segments, we don't even have to think about the diameter in particular for this proof. We just want to prove that XA times XB equals XC times XD. And well, simply we can observe triangle similarity with angle chasing. From angle chasing, we know these angles are equal. And this angle is equal to this angle. The blue angles are because of the arc AD. Look at the arc AD. You have the blue angle ABD, and you have this blue angle, outside blue angle ACD. And the green angles are from the arc BC. So you can say XAC is similar to XDB by angles. Yeah, let me just say by angles. By angles, XAC equals. By the way, maybe better notation is to call them M and N, because to emphasize different roles. The first thing is by angles. XAM is similar to XNB. You see there is a flipping here. So this shows that XA divided by XN equals, now in the next fraction, the denominator and the numerator are flipped in terms of the letters. So XM divided by XB. And this shows XA times XB equals XM times XN. So in the proof, we observe this triangle similarity. What triangle similarity we observe? We take the point X, we take one of the points A and B, and we take one of the points, M and N. We look at this triangle. It will be automatically similar to the other triangle in the opposite direction. And this will give me what I want. So instead of XAM, I could also look at XAN, by the way. There is no difference because they have the same role. You know, there is permutation symmetry of the labels. You can think about it. Permutation symmetry of labels. I could call this one M, this one N. So it should really give me alternative. So the proof is already finished, but I just want you to see this from all different perspectives, all the possible ways. To see that it's not a different proof. All right? Alternatively, we can start with XAN similar to XMB. But this is by permutation symmetry, it's the same thing. But in the picture, it looks different. Maybe the angle chasing of this looks different in picture, but they are the same things. Anyway, but this time you would have XA over XM equals XN over XB, and you would still have the same equality. So if one of these is the diameter, you can get this equality, and you can see that all of these are equal to the power. But we did this when x is outside the circle. So all in the pictures that we did, x is outside the circle, but it doesn't matter when x is inside the circle. What you should know is that the power is negative. Okay, when x is outside the circle, the power is positive. When x is inside the circle, the power is negative, obviously, because xo is less than r. When x is on the circle, power is 0. So by definition, the circle itself is the set of points at which the power is 0. So note that x is on the circle gamma if and only if power is 0. So power is in some sense, generalization, a quantitative generalization of the incidence relation between points and circles. As I told you, geometry in this geometry consists of figures. Figures consist of points, lines, circles, and the relationships between them. And what are the kinds of relationships? As I said, lines could be parallel, lines and circles could be tangent, and points could be collinear, etc. All sorts of relations. And there are the incidence relations. A point could be on a line, a point could be on a circle, etc. So power is a quantitative measure for when to identify when the points are on the circles, in some sense. When this is equal to 0, the point is on the circle. When it is not 0, it's not on the circle. So this is an algebraic equality. The condition that the point is on the circle is defined by an equality. But the condition that the point is outside the circle, it's an inequality. The power is positive. When the power is positive, the point is outside the circle. When the power is negative, the point is inside the circle. But this doesn't matter. As I said, inequalities don't really matter for the statements. But this fact is generally true. When you draw any line through the point x and let it intersect the circle at a and b, xa times xb gives the power. And let's draw the same thing when x is inside. And let's also, draw the diameter, for example, as we did here. So in this case, xa times xb is still equal to xp times xq, but xp times xq is minus the power, okay? And as I told you, if we use directed lengths, it will not even be. So we will not even need to put the minus, because the minus really comes because xp and xq are in different directions in this case. So it naturally brings the minus. And in this case, they are in the same direction. But if you don't think about it like this. So this is the power formula. So this is by definition. You see that this is by definition, and this is by the proof above. All right, this is our first fact about the power. This is something probably all of you already know. The next important fact is when we try to write some equalities using power and look at the geometric interpretations of those. Okay. When we say that power of x with respect to gamma is equal to something, like in here, when it is equal to 0, the geometric interpretation is that x is on the circle. Other things is to take two different circles and say the power is equal to power of a point is equal with respect to the two circles. Consider this. So given gamma 1 and gamma 2, given the circles, given two circles, gamma 1 and gamma 2, this has center O1, R1, and this has centers O2, R2. This becomes an equation for the point x. So what does this equation tell me about point x? This is the question. Given the two circles, okay? Given the two circles, what does this equation tell me about point x? This is the question. So let's just really focus on the equation. Let's try to understand it. Let's begin understanding. So xo1 squared minus r1 squared equals xo2 squared minus r2 squared. So it's natural to bring the x terms together. So this really says xo1 squared minus xo2 squared equals r1 squared minus r2 squared. So this thing is just a quantity, right? On the left side, notice centers and the radii are separated now in this formulation of the equation. So I just have points O1 and O2. Given points, fixed points, O1 and O2, they are given. R1 and R2 are also given, but from R1 and R2, all I need is just this expression on the right-hand side. So basically, I am given this quantity, just any value. And the points O1 and O2 are given. What we are trying to understand is xo1 squared minus xo2 squared as an expression. When we set this to a constant value, what set of points does this give me? And this is where squaring becomes important, because if you write this in terms of coordinates, you will actually see that this becomes a linear expression in the coordinates of x and y. When you subtract these squares, the quadratic terms cancel each other. This becomes a linear expression. But geometrically, we can see it like this. If points O1 and O2 are the same, by the way, this is impossible. If the left-hand side would be 0 and the right-hand side, if they are not the same circle. And if they are the same circle, of course, all the points would satisfy. Right? So the for non-degeneracy, we must suppose O1 and O2 are not the same. In this case, for a general point x, really, xo1 squared minus xo2 squared is simply if you draw the perpendicular from x to O1, O2, if you call this t, it is gonna be equal to one can write a formula like xo1 squared equals xt squared plus to1 squared, and xo2 squared is also xt squared minus to2 squared. So xt's would be cancelled. So this is just equal to to1 squared minus to2 squared. And if you also look at the point M, which is the midpoint of O1, O2, you can write this as, I mean, if you do the calculations, you can see that this should be equal to what 2 times Tm times O1, O2, I think, something like this. But what I want to basically say is, suppose O1, well, okay, let's not complicate this one, but let's, I'll try to explain it in the simplest way. What I want to show is xo1 squared minus xo2 squared equals, anyway, to1 squared minus to2 squared. And at least we can understand that as t moves toward the right side, this increases. Right? As t moves towards the left side, this decreases. Even if it passes O2. And in a linear way. This is a linear expression in t. I mean, if you think of this as the real line and put the coordinate, put just one coordinate. I'm not talking about 2 coordinates on the plane. Just put the real number from any origin. You can choose any origin here and put the coordinate for t. You will see that this is a linear expression. But you don't even have to see that it's linear. It's not. You just have to see that it's increasing. So let me just write this because at least really what we need to see is that given this value, t is uniquely determined. Well, if you are not convinced, tell me, by the way. I mean, if you're not convinced, definitely tell me. Given this value, if this value is given, like in here, in this case, the value is given, whether, negative or positive, the value would uniquely determine the point t. Is this something you're convinced about or not? Now, I can say more strongly, the expression is linear in t, but this is not exactly. This is stronger than what I need, right? But you can easily, write the coordinates and see that it's linear. When it's linear, you can just solve it. So what does this tell me? Essentially, in conclusion, this relation, power gamma 1 x power gamma 2 x, determines that xt is perpendicular to O1, O2 for a given point t. How is this given? Given by this relation. Given by this, right? When you write this equality, point t is given, so it just determines xt is perpendicular to this. So the set of points that it defines is really this line. It is a line. Now, more generally, when you write the difference between the powers. So as I said here, when you just write the power of a point x with respect to a single circle, And when you say it is 0, it means x is on the circle. When it is positive, x is outside. When it is negative, x is inside. Here, when you write the difference of powers with respect to two circles with the same point x, when it is 0, x is on a certain line. When it is positive, x is on one side, and when it is negative, x is on the other side. So let me write this like this. So given gamma 1 and gamma 2 with different centers, with distinct centers, O1, O2. Okay. There is a line L, which is perpendicular to O1, O2. This line is called the radical axis. Such that powers are equal if and only if x is incident on this line. So this is our theorem about the radical axis.
Could we have that whenever a power of a point of x with respect to gamma 1 minus power of a point of x with respect to gamma 2, the difference between them is constant, then could we make sure that x is always in some line
Exactly.
uh,
Exactly. So this is
perpendicular?
just a special case. So when you write power of gamma 1 x equals power of gamma 2 x plus 1, for example.
The same thing.
Yeah, this is also a line because, well, you can think about it just as this. Because power is simply just a distance squared with a certain offset. So if you just put a constant here, what you are doing is you can change the radius of the circle, gamma 2. You can maybe increase the radius of one of them or decrease the radius of one of them. So it will be a new circle with the same center. This time the powers will be equal. Okay. Yeah, exactly. Exactly. Power of in general, yeah, when you have two circles, power of gamma 1 x minus power of gamma 2 x. When you set this to a constant value, this gives a line. As the constant moves, you have a parallel family of lines. And let's draw pictures of this. This is the nice and important thing. Okay. When you have two circles like this, the radical axis in this case has to be between the circles. You can sense this, I think, easily. It's more like this. Okay. So because this circle is bigger, distance of O1 to the line is bigger, but distance of the circle is smaller on this side. Okay. So this is the radical axis L. So when x is on this side, power with respect to this circle is less than power with respect to this circle. And when x is on this side, the power with respect to this circle is less. For example, when you say exactly that the power difference is 1, it will be a line like this. When the power difference is 2, it will be exactly 2 times the distance. So those lines also, the power difference is really a linear formula in the point x. These lines are perpendicular to the common diameter. In this case, the line goes outside of both circles, so the powers are positive. Let's draw other pictures when the circles intersect. Now, the nice thing is when the circles intersect, these two intersection points are automatically satisfy the equality because 0 equals 0. So the line has to be this one. This is really a nice situation. So you know that the powers, so this is used really to prove collinearity in a lot of problems. When you just prove that the power of a point is equal with respect to this circle and this circle, you automatically prove that this point is collinear with these 2 points if you have the intersections. Or sometimes in general, if you just have 3 different points and prove that the powers are equal, it proves that those 3 points are collinear. So this is one way to prove collinearity in geometry. You can also have intersecting circles with which are like this. In this case, the radical axis is here again. Okay, it will be of course perpendicular to the common diameter, right? So these are O1 and O2. So one nice thing, by the way, is to look at this from the other direction. Namely, when you look at this as an equation for the circle, when you fix the 2 points, but it's not gonna be exactly this. But what I mean is, when you fix a point x1 and say that the power of gamma, sorry, power gamma x1 is a given value, and power again gamma x2 is a given value. How does this determine the circle gamma, which is, I mean, let me not say it in this complicated way. What I mean is, okay, let's look at these pictures, and from these pictures, I think it will be clear what I mean. What I mean is this. So when you have 2 circles, for example, let me draw the tangent situation. When they are tangent, what is the radical axis? What do you think is the radical axis? It's the common tangent, right?
Yeah.
This is the radical axis. So what I mean is, can we draw, for example, this thing that we drew on the previous page? This nice picture. Whenever you have, a point and a direction, when you have a line and a point on it, the set of circles that are tangent to it, tangent to this line at this point, gives me what is called a pencil of circles. This is a special kind of pencil. And what is more general is when you have a radical axis, common radical axis. Common radical axis, and together with the given values of the power. So when the radical axis is given, for example, when you take any point x on this, you know that the power of x to this circle and power of x to this other circle are the same. So can I basically draw other circles in between? So to extend this to an infinite family of circles that I can call power, so that all of them will have the same value of power with respect to point x. And not only just this point x, but all points on the same line L. So this is the generalization of this thing about tangency. Because, for example, in this case, those will be the circles that will pass through these 2 points. So this is the notion of pencil of circles, okay? The notion of pencil of circles. the general notion of pencil is this. Pencil is an infinite family of circles which have a common radical axis. Pencil of circles is an infinite family. But to be precise, it's a one parameter infinite family. Anyway, infinite family of circles with common radical axis. This I can say is the definition. Okay, all of them share a radical axis, so any two of them have the same radical axis. So let's draw pictures of this. The picture would be like this, you know, you would have circles. So as the circle approaches the line, circle gets bigger and bigger. And on this side, similarly, and as they get smaller, so they degenerate to some points. So this is one kind of pencil. With common radical axis. So from this you can see when I said that this is a picture of pencil of circles, then this is a special, really very special picture when the radical axis is tangent. In general, whenever the radical axis is common, we call it a pencil. So there are, we can say, two types of pencils. One in which they don't intersect, so pencil of non-intersecting circles. So this is an example of pencil of non-intersecting circles. Both of these are examples of this. And pencil of intersecting circles. Although algebraically speaking, their properties are the same. There are some differences in if you. This one is maybe geometrically more easily seen, right? So you can see that there are two conditions on the circle, for example. This one makes it explicit. There are two conditions. So it passes through this point and this point, for example. Anyway, yeah, we have lots of circles like this. So when you have these two conditions, there is still one free parameter. So all the centers are collinear, of course, but not only that the centers are collinear and centers are this line is perpendicular to the common radical axis, but as the center moves, the radius also moves in a certain way, follows it with some formula. Okay. Anyway, so this is the notion of pencils. But of course, the notion of pencil is a more advanced notion, but radical axis is a fundamental notion. The radical axis is really a very basic notion that you absolutely must know in Olympiads. Pencil is, let's say, an advanced notion. So this is the second fact that I discussed. The first fact is just the product of the segments. The second fact is the radical axis. And the third fact I want to discuss is when you do this with three circles. Again, what does this tell me about X? So this time you kind of have two conditions on X. So when you, in the previous case, you put one condition and that this gave a line. This time you're giving two equalities. So this should be intersection of lines.
So we know that X lies on the radical axis of circles 1 and 2, the radical axis of 2 and 3, and 3 and 1.
Yeah. So this says basically X, simply because we have solved already one equality case, it geometrically corresponds to a radical axis. So this basically tells that X lies on the radical axis of gamma 1, 2, and gamma 1, gamma 2, gamma 1, gamma 3, and gamma 2, and gamma 3. So this basically says, well, again, let's suppose for the non-degenerate case, suppose O1, O2, and O3 are not collinear, okay? So let L1, O1, O2, O3 are like this. Let L12 be the radical axis of gamma 1, gamma 2, and L13 similarly, gamma 2, gamma 3, sorry, gamma 1, gamma 3, and L23 similarly, gamma 2, gamma 3. So from this we have X is on this line, L12, L13, L23. So the condition is this, but the condition is in fact any two of these. When two of these are satisfied, the third is automatically satisfied. Because when L12 and L13, when X is on L12 and L13, we have this equality and this equality, so the third equality just comes by itself. This is the important thing. When two of these are satisfied, the third is satisfied. Now, what does this tell me about X? X should be the intersection. So the important thing is the reason I assume that they are not collinear is now L12, L1, L12, L13, L23, they are not parallel. Okay? Because they are perpendicular. L12 is perpendicular to O1, O2. L12, L13, L23 are not parallel. In this case, there is an intersection between any two of them, and that should be X. But the intersection between any other two is also X. So these are definitely concurrent. Right? Which means L12, L1, L12, L13, L23 are like this. They have unique intersection. This is called the radical center. Radical center of three circles with points not with centers not collinear. So given any three circles with centers not collinear, there is the notion of a radical center, and there is this theorem that the three radical axes are concurrent. So let's draw pictures of this theorem, which is nice. For example, if you draw with non-intersecting circles, means somehow, there are these radical axes that are concurrent. But especially when we draw it with intersecting circles, this is a picture that you can draw without knowing anything about geometry. Even children can draw this. But in this picture, somehow it is remarkable that these three lines must be concurrent. And this is true. And the proof is through this, radical axis. It has to be like that. So what if the centers are collinear? In this case, the radical axis will be parallel. So what can you say? What can you say? When the radical axes are parallel? When the centers are collinear, the radical axis will be automatically parallel because all radical axes will be perpendicular to that line, right? When O1, O2, O3 are parallel. So let's call this I, situation I. Or A. B. Suppose O1, O2, O3 are collinear. So that is, let's say all of them are on the line M. Let's call it line M. So all these radical axes are perpendicular to the same line. Well, there are two situations here. Can you tell me what the two situations are? Two different things that can happen.
Maybe two of the radical axes could coincide.
Yeah, if two of them coincide, the third one must also coincide.
Yeah.
Yeah. Or they don't coincide. These are the two different situations. So either three of them coincide, which means that the three circles are on a pencil. So either the circles are on a pencil, either three circles. So when the centers are not collinear, the circles are also not on a pencil. Being on a pencil is sort of like a hyper notion of collinearity for circles. If you think of circles as themselves represented by points in some three-dimensional space, being on a pencil here in the two-dimensional plane corresponds to being on a line, being the representative points being collinear on the three-dimensional space. So for this, it is necessary that the centers are collinear, but not sufficient. If the centers are collinear, and then moreover, if the radii also satisfy some relationship, then the three circles will be on a pencil. In this case, there is a radical axis, common radical axis. Otherwise, when the 3 points are collinear, but if they are not on a pencil, there is no radical axis or no radical centers, no point of no solution for this equality. But when the centers are not collinear, this is the non-degenerate situation, this is the general situation, there is a single radical center. So in this case, either these are on a pencil, then L, so there is one radical axis. All of these are the same. or they are not on a pencil. So L1, so these are now parallel lines, parallel distinct lines. So there is no X. That satisfies. In this case, there's no solution, right? So in this case, X is on L if and only if. The non-degenerate situation is the most common situation, of course, is the generic situation. Generic situation. All right. So this is what I was gonna present about this. So we can solve one problem, I think. This has become very tiring, 2.5 hours non-stop, but let's just solve one more problem. So in this problem, there is circle, well, triangle ABC and circumcircle, okay. And there is a circle gamma, so circle omega, which is tangent to the circumcircle at point A. And this intersects, it's given to intersect AB at K. The intersection is K. So we draw a tangent from C to the circle, tangent at L. All right. Maybe it is better if I leave this as exercise for you, okay? And as homework for tonight. So hopefully we will have, is everyone available tomorrow at the same time?
Yeah, it's okay. I'm available.
What?
Yeah, it works for me tomorrow.
Yeah. So, okay, let's meet at the same time tomorrow. But if I decide to change the time, I will let you know. But otherwise, let's meet at the same time tomorrow at 12, tomorrow, inshallah. So this will be homework for you. And in the beginning of the lecture tomorrow, we will hopefully solve this. And we will start talking about triangles. So CL is tangent, you can see. L is on omega. So this point is T. So show that the length of the tangent drawn from B to omega. What is meant by this? When you draw a tangent line from B to omega, the distance from B to the tangent point, you can draw it from here or from here. You know that they are equal, right? So it's in fact good to draw this on our previous page when we discussed the first fact, when we discussed the very first fact about powers. You can draw the tangent line as well, by the way. When you draw the tangent line, do you see what happens? The points A and B become the same point. They are both t. So this becomes xt squared. This only happens when the point is outside. When the point is inside, of course, you cannot draw a tangent. But when the point is outside, you can actually draw a tangent. And this is also equal. The reason this cannot happen when x is inside is that this is something squared, so it is positive, right? So this tangent or the other tangent, there are two tangents that you can draw from a point outside. They have equal lengths. So the question says that this length, prove that this length is equal to bt. Show that the length of the tangent drawn from B to omega is equal to bt. This is what it wants you to prove. Now, I didn't set the picture. There are alternative pictures that you can draw in this problem, and I highly recommend to draw the alternative pictures. But I want to tell you that in the original exam that I took this problem from, it was a Russian Olympiad. Of course, they don't want different pictures. I told you this before. In Olympiads, they don't want students to draw different pictures because this is hard for the coordinators. And they want to fix the picture. They add information to the problem just to fix the picture. And that information doesn't help you in solving the problem. But that information usually comes in the form of inequalities. So you can extract it. You can understand that, okay, this information is really for the picture. And it should not be important for the solution. So I can ignore that information and draw alternative pictures for myself. For myself to solve the problem. But when I write the official solution, when I write the solution, actually, of course, I must obey the extra information they give. So in this problem, the extra information that they gave, which I removed in this case, was that the circle omega intersects the segment BC. Okay, what they said is that, yeah, circle omega is tangent from inside the circumcircle ABC. Is what they said. So it's tangent from the inside, and it is big enough that it intersects BC. And now when it comes to point L, as you can see, is the point L uniquely defined here? No. There are two alternatives for point L. But they said that the point L is under BC. It's on the opposite side of BC as point A. In this case, it is impossible for it to be. I mean, if the red circle omega is small and it doesn't intersect the segment BC, then both points L are above the line BC. But when it intersects, one of them will be under. So they said L is the one which is under that. Now, with this extra information, as you can see, when the red circle is big enough that it intersects the segment BC, and while L is under, everyone draws the same picture. But is this needed for the solution? No. red circle could be tangent in any way, and point L could be any of the 2 points. Okay? The problem should still be valid. So once you understand this, you can draw lots of alternative pictures. And those alternative pictures can help you understand the solution. Maybe one of the pictures will be easier for you to solve the problem. And once you solve it in one of the pictures, you will just convert it to the other picture, to the picture that they want. Okay? So this is exercise for you. If you solve it, send your solution to me on WhatsApp tonight. Hopefully I will read it tonight or tomorrow morning. Do you have any question?
I have a question about geometry and Olympiads
Yeah.
overall. Assuming we have a question that can be solved through 3 claims: claim 1, claim 2, and then claim 3.
Yes.
But they depend on each other. Like, to show claim 3, you need claim 2, and to show claim 2, you need claim 1.
Yes.
Let's say, for example, I'm able to show claim 1, and I know how to show claim 3, but I can't prove claim 2. Can I just, like, and if I were to assume that claim 2 is true, and then prove claim 3 mathematically, would they count you points for showing claim 3, or since you used an unproven claim, they don't count it?
No, they can give you points for sure. If it all depends on the significance of claim 2 with respect to the whole problem.
Mm-hmm.
So if the difficulty of proving claim 2 is almost as difficult as the whole problem, then they would not give you any points for claim 1 or claim 3. But if claim 2 is somehow, let's say, very easy, but you just didn't see it, it's really very easy, and the big part of the solution is claim 1 and claim 3, and you did this, you just didn't bridge the gap, then they can give you a lot of points for that.
Okay, thank you.
Yeah, it doesn't have to be like an unbroken chain. Yeah, it can definitely be like this. Other areas also, I mean, this can also happen in combinatorics, number theory. It can happen in all of them. But what usually, especially in geometry, this happens a lot in the bad way that I said. I mean, especially when they do computational solutions. There are, computational methods in Olympiad geometry. One can use trigonometry to calculate the side lengths and to even find angles, find angle equalities from the ratios of the side lengths, and do sort of angle chasing in this manner using trigonometric calculations. And ultimately, they can prove lots of claims, collinearity, concurrency, lots of things can be proven using trigonometric calculations. And this is one of the methods only. And there are coordinate methods, which are usually called bashing the geometry. So when you use some sort of coordinate system, and this also has divisions under itself, because there are different kinds of coordinate system: complex coordinate system, Cartesian coordinate system, barycentric, etc. Complex is the most common and the best one. With any of these computational methods, well, especially with trigonometric one, in my experience, what some students do is they take the given information in the problem, they formulate it trigonometrically, and they somehow do algebraic manipulations, and they get some equalities. And at the end, there is something that they need to prove, and they write it also, they formulate it also trigonometrically, and it's they want to also manipulate it algebraically and somehow bridge the gap, right, from this equality to this equality. But they cannot do it because it becomes sometimes very complicated. And they say, I have sort of done the claim 1 and the claim 3 part of this. They sort of want to argue it like this. This is never accepted. For computational things, when it is not complete, they give you 0. But for the synthetic parts, as you say, if claim 1, claim 2, claim 3 are all themselves geometric statements, then no problem. If claim 2 is easy, they can give you lots of points for claim 1 and claim 3. If claim 2 itself is not a computational claim, if it's a geometric claim, claim 1 itself can also be proven computation, no problem. If it is completely proven, it doesn't matter whether the proof is synthetic or computational. They will count it as complete. Each subpart, each complete subpart can be computational or synthetic. But the incomplete parts, the gaps, cannot be computational. If there's a computational gap, they consider it to be invalid. But if there is just a synthetic gap, then they will give you marks appropriately for the proven parts. These are the rules in IMO. But I recommend you to learn the computational methods as well, because, well, you have 2 weeks, and in this week, hopefully I want to have, as I said, inshallah, tomorrow we will have another lecture, maybe hopefully the day after that as well. So I want to have several lectures with you. This is my goal, but I don't think I will have any time for the computational methods. But you can just learn from the online sources, complex bash, at least, for example. You can learn this just spending 1 day on it, 1 or 2 days on it, you can learn it. And it can be useful, maybe, to prove at least subparts of the problem, maybe not the whole problem, but subparts. Usually, synthetic way of solving is easier. But sometimes, when you cannot see, having an alternative way can be helpful. So if you just find the opportunity to learn, I recommend it. All right, then see you tomorrow. If you don't have any other question, inshallah.
See you.
Yeah.